Okay, welcome back. This is the example program, Unit D1, page 6. This is essentially the exact same program we looked at in the previous example program. This is the bathtub. Water is filling up the bathtub. Then we want to know the rate of change of this water depth h dh dt in terms of inch per minute. Okay? So let's take a look at once again. Solve the problem, a previous example we looked at, using a deforming control volume that includes only the water accumulating in the bathtub. Okay. So let's take a look. So this is exactly the same problem statement. So now, again, this is the figure I copied from the program statement. Now, the significant difference from the previous approach is the definition of control volume. Remember, in the previous program, I defined the control volume as the volume of bathtub itself, which is fixed control volume. Now, in this case, I'm going to define my control volume as only a water inside of this bathtub. Okay, so this is my control volume. Obviously, this is a deforming control volume. Water only. So as you keep adding the water from the faucet, this volume keeps changing, increasing. Okay. What is the deforming control volume? Deforming control volume is the control volume which one of the control surface is moving with the finite rate of velocity, VCS. This VCS is essentially velocity dh dt. Let's define dh dt as a velocity vector, which goes upwards. Okay. And where is the control surface, by the way, in this case? Remember, the control surface for the case of fixed control volume is where this top surface cut across this incoming stream. Now, in this case, where is the control surface? Control surface is right here. Okay. Right here on the top surface of this water, where the water incoming and keep filling up. So this is the control surface. So control surface is, of course, different because the control volume definition is different. Okay. Now, obviously, this control surface is moving upwards with the velocity dh dt. All right. And of course, don't forget the velocity of incoming stream. This is the velocity vector Vj coming down. Then of course you are going to obviously define outward unit normal vector Nj also. Okay. So one significant difference is, of course, the definition of control volume is different. Because of that, location of the control surface is different. And then now in this case, control surface is moving upwards. Okay? So I want you to go back one page and let's take a look at again deforming control volume. So when you apply the solution of deforming control volume, you need to recognize that you cannot use the velocity v. This is absolute velocity, which we're using all the time. Velocity relative to the coordinate system, which is absolutely not moving, which is usually fixed to Earth. It's called inertial coordinate system. It is a velocity relative to that. But suppose if the control surface is moving, relative against the control surface which is moving, you do feel a different velocity, which is a relative velocity. Okay? So we have to redefine our continuity equation in terms of relative velocity W. Okay. Now obviously relative velocity W is velocity V is equal to W plus BCS. So vector relationship wise, so that's the relationship. Relative velocity added together with velocity of control surface, which is moving control surface, is going to be absolute velocity. So this really means that, how do you get the W? Well, W can be given by B minus BCS. No, it's not true. W is given by absolute velocity added together the negative of BCS. This is the vector calculus basics. So in other words, in order to find out W, what do? Velocity B, and this BCS need to be flip-flopped. This is a BCS, flip-flop the direction, in other words negative. Then if you add this velocity and this one, add them up, then you can determine relative velocity W out of it. So in order to determine relative velocity W relative to the moving control surface, you have to flip-flop the velocity BCS. Then that flip-flop the velocity BCS is added to the velocity B to get the W. So let's apply this situation to that. Okay. So let me just right here. Let's just zoom in around here. This is control surface which is B sub J. Okay? So this one is moving upwards. Of course, that's the velocity is control surface. Velocity of control surface, BCS, which is magnitude-wise dH dt. So this is dH dt velocity and going upwards as a vector. Okay. This is incoming velocity B. Velocity B, in this case, is B sub J, coming down to here. So out of this situation, you want to find out W. Okay? Let me just change the color here. This is B. This is BCS flip-flopped. This is W. So how do you get W? Well, of course, this BCS need to be flip-flopped, then added together. Okay? So this BCS flip-flopped. This is dH dt, direction downwards, adding B sub J. Add them together. Then that is going to be W, relative velocity, W. This W. So this W really is obviously magnitude-wise, magnitude of Bj added together magnitude of dH dt. This is a velocity vector with the magnitude of Bj dH dt added together, direction is going down. Okay? So obviously this W need to be dot product against outward unit normal vector. Okay? So here is the equation, let's rewrite the equation. Okay, continuity equation. In terms of relative velocity. Integral over control volume, ddt, integral over the control volume rho dv, plus integral control surface rho times w dot nda is equal to 0. So this one, w dot product n, w dot product n, in this case, vector of opposing. So this is going to get you minus of bj plus dh dt. Negative because it's negative opposing each other, and then this is the magnitude of w. Okay? So let's move on here. So this equation now becomes, this is ddt of density again, rho of water, and then this is an integral over control volume. Integral dv is a volume. This is a volume within control volume, which is volume of control volume itself, which is 5 feet times 2 feet times h. Right? So this is going to be 5 feet, 2 feet times h. So this is a volume of water inside of the control volume, which is volume of the control volume itself. Density of water. That's this. Okay. Notice the difference from the previous example? I hope so. Then this one now becomes rho of water once again. Dot product gets you minus bj plus dh dt that's the dot product. Integral over the area gets you aj. Adding those two together equal to 0. Now again, the same thing. This rho of water is constant, so it goes outside. You can divide both sides by constant density of water, get rid of that. So left hand side becomes ddt of 10 feet square times h. That one, let's move it right hand side, which is bj plus dh dt aj. Right? Okay. So this is 10 feet square times dh dt, which is equal to b sub j a sub j. This is a sub j times dh dt. Bring this one to the right hand side. dh dt 10 feet square minus a sub j is equal to b sub j a sub j. B sub j times a sub j. This is flow rate. Q 9 gallons per minute. We know that. So this concludes dh dt is equal to flow rate Q divided by 10 feet square minus aj. Oh, exact same equation we got. So obviously this is going to be inch per minute, time rate of change of h. Water depths. Or this is the velocity of water surface moving upwards. As you notice, this is the exact same equation we got. Okay, so obviously this program you can solve using fixed control volume, which is the bus stop itself, or you can solve this problem alternatively, defining deforming control volume, which is the water only, water itself within the bus stop, being a control volume, which is deforming. Okay. Now, deforming control volume comes with one of the control surfaces moving with a finite speed, which is BCS. So that surface is moving. So suppose if you pick up a, I don't know, wooden plate, then you stand up on the wooden plate. Okay. That means you are moving upwards with the speed dh dt. That's the speed you feel while you're actually moving upwards. So if you are standing on the plate, okay, so as the water comes in and volume increase, you moving slowly upwards like this, okay? Then at the same time you see this velocity of water incoming. So velocity is incoming. This V sub j is incoming. You are moving upwards by watching velocity incoming. So what is the actual velocity you feel? Velocity adding together, right? This is relative velocity. Relative to the coordinate which is attached to the moving control surface and moving with it. Okay? So that's called relative velocity. So in this problem, which is significantly easier math, however, the point is being what is W? So you have to go through vector calculus process, obviously. Vector calculus process to determine what is W. Then use that W into your equation. Okay? The rest is much, much simpler mathematics than fixed control volume. Okay? So let's stop here.